Thanks for coming, and hopefully you had a good lunch. So let me, first of all, I'd like to point out, actually, even though in the program and everywhere else, I'm still at UCSD. I'm actually at the Lloyd Institute for Brain Research in Tulsa, Oklahoma. I still have an affiliation with UCSD, but just to kind of let you know, that's where my current coordinates are. These are my disclosures, really not much to speak of. So let me give you an outline, and also let me give you a sort of my background so that you see where I'm coming from. So, by training, I'm a psychiatrist. I've been doing a lot of neuroscience-based research in psychiatry, and I've always been interested for actually over 25 years now into, at that time, it was mostly dynamical systems, and then later on more computational systems and computational approaches to psychiatry. And the main motivation here is that I've always been driven to understand what are the underlying principles of the dysfunctions that we're observing. And how can we put them into a context that we can make them quantifiable? And so for me, that's led me to, for example, looking at dynamic dysfunctions in various disorders, and more recently into sort of more process dysfunctions. I'll make this very concrete in a moment. But I think I'm very happy to see computational psychiatry having a resurgence. And all I'm hoping, and I will talk about this at the end, is that enthusiasm and optimism will carry us to actually make actionable and useful insights. So I will talk a little bit about something that came up yesterday in a presentation, which I really like, which is sort of the playing off one versus the other types of framework, what I call the explanatory or pragmatic framework. And you'll recognize there may be slightly different words, but you'll see exactly what I mean in just a moment. I will talk about computational failure modes, and we've already had some discussions yesterday. David brought up the notion of a failure mode, and we've had some discussions. What is actually the right term? I'm not wedded to the term failure, so then that may be something we can discuss tomorrow at the group session. And then I'll give you 4 examples of a computational failure mode in a particular condition, or in a particular group of people who have problems with anxiety that are clinically relevant. And I'm describing it this way because over the last 5 years, we've taken very much a transdiagnostic dimensional approach, and I'll make that clear in a moment as well. So I'll be talking about how anxious versus non-anxious people differentiate signal from noise in a change point detection task, how they adjust current and future errors in a movement task, how they play off perception versus decision-making processes in an uncertain environment, and finally, how they arbitrate approach avoidance situations. And there are, and I want to say, there are some common and converging themes, but it's not exactly completely gelled yet. So this is still, I would consider, work in progress. So I wouldn't want to say that we fully understand what the basic processing dysfunctions are in anxiety. And then finally, I'll put a pitch in for something that Quentin Hoyes and Michael Browning and Tiago Meyer and others that we've kind of been pushing, which is sort of applied computational psychiatry, and I'll sort of give you an outline of what I mean by that as well. Okay, so a number of years ago, I wrote a little piece where I was trying to kind of take a step back and remind ourselves why we're doing what we're doing. And when I say we, I think of myself as primarily a problem solver and a clinician. And so, in a way, we have to think about it. We're trying to solve problems, but whose problems are we trying to solve? Well, we're trying to solve the problems that the stakeholder asks us to solve. So who are the stakeholders? So, well, the stakeholders I call the 5 Ps: patient, providers, payers, policymakers, and problem solvers. And if we're honest with one another, many times we actually solve problems mostly for ourselves. for our peer reviews, for our study sections, and then for our peer review journals. But I want to remind ourselves, really, we want to make people's lives better. I mean, at least that's what I think as a biological researcher. And I do think we need the disciplines. We hear in the applied and pure, in the pure and applied mathematics building, I do think we need people who are theoreticians who think about problems in trying to extract principles. And that's what I'm hoping that people will get excited about when I show some of the data, because it's not me that's going to come up with these quantitative principles. It's going to be you guys. So the thing is that once you have these demands, then it's a second step to think about what are actually researchable questions. And this is actually something that's often underappreciated. The notion is we can ask a lot of questions, but which ones are really researchable? And how can we actually bring a design to that question to actually answer it? And then, and this is again something that we heard about yesterday. I think we should be clear about what the primary goal of our researchable question should be. Is it an explanatory goal, or is it a pragmatic goal? And let me expand on this a little bit. So for quite some time, I was almost always emphasizing this part, which is the pragmatic goal. And we heard yesterday about how difficult it is to come up with machine learning based models that do robust predictions, and that the prediction metrics may not be the same as the statistical significance metrics. And so in a sense, this is sort of this distinction. When you're going for a pragmatic goal, really what you're after is, from my perspective, is predictions of various sorts. And your measurement of your predictions really should be accuracy and robustness. And we all know how difficult that is for a variety of different reasons. And then the other element of it is predictions alone, from my perspective, are not enough. They're useful, but we need to then think about what are the actionable outcomes. And this is something that actually, so for example, even if we do weather prediction, right, the actual outcome is what kind of clothes you're going to wear. I write to work every day I'm at work, and I look at the weather app every morning because I need to know what the weather is to basically, that's an actionable prediction. But oftentimes we make predictions, say, about diagnoses, or even about outcomes of particular diagnoses, but we don't really know what the actionables are. And so that really is something that we need to think hard about. Now, on the other side, and I think we had a bit of a discussion about this yesterday, we also want to build explanatory disease models. And I initially, quite frankly, I underappreciated that. Because I said, and this is primarily because it's so difficult to identify mechanisms in the whole patient. It's easier, or it's more rigorous in an animal model where you can do molecular manipulations such as threads or optogenetics, where you can really nail down what are the causal links. In humans, it's so much more difficult, in some cases impossible. However, it turns out that if you, and this is interesting, not a lot of people have actually asked patients what they want from research. There are actually only a few studies have done this. And the few studies have done this, one of the top level ask for the stakeholders is, of course, research should come up with something that makes me better, but research should also help me understand my disease. It should provide an explanatory disease model. And right now, I mean, quite frankly, I can tell you as a practicing psychiatrist, we use disease models that have nothing to do with reality, quite frankly. We talk about serotonin dysfunction, we talk about dopamine deficiencies and whatever not. The truth of the matter, this is not even a crude approximation of what's going on. So I think when we talk about computational psychiatry, and if we talk about computational models, then we also should think of them as true explanatory, empirically based disease models. And so today I'm going to talk a little bit more on this side than actually on that side. And in that case, of course, when you get to explanatory disease models, you really are held to the levels of causality and how deep can you go. And this is, for example, work that David and David in collaboration is doing is so wonderful, because he can do things in animals that we can't do in humans, which then really gets us to a much deeper level of causality. So I basically just walked you through this. Just sort of give you my view of what I see as computational psychiatry, and in contrasting how the landscape has changed. I would say the old approach, and again, it's an oversimplification, is essentially we observed a certain behavior, and we basically looked at that behavior during scans or other biological measurements, and then somehow we created a correlational association to basically say, oh yeah, if this behavior is in such a way, we see, say, a blob in the brain, so roughly speaking. What I think computational psychiatry has added to this is that we're making explicit of how we think about that this behavior is instantiated, and then ask the question, okay, if it's instantiated this way, then can I map it back onto something that has something to do with biology? That's really what we're trying to do with the computational approach. And there's lots of steps involved, right? So what's the right model? How do we compare models? How do we say that, how do we map the model parameters onto the brain measures? So it's not that, it's not that straightforward. But I think this is sort of the way I think of computational psychiatry, as opposed to just basically say we take two sets of variables. This can be useful for a pragmatic prediction, but I think this is something that we need for explanation. So let me talk a little bit about something that I've recently sort of written about, and also gives you a little bit of a framework of what kinds of models we're thinking about. One of the interesting things, and you've seen a number of computational models over the last 2 days, what's actually not as well appreciated is most models of learning have been focused on reward or positive valence learning. In other words, you get something and you do something right and you get a reward. The truth of the matter is, if you think about it, even from a day-by-day perspective, we actually encounter a lot more events where things are not going well, and where you have to learn from things that have adverse outcomes. And we know this from the old Kahneman and Tversky studies. Losses loom larger than gains, and these have profound influences. So I would emphasize that one of the things that I'd really like to see more of is to have people look at what I call aversive related decision making, or paradigms that are focused on how you adjust your behavior based on an aversive environment. And I'll walk you through a couple of examples of how that can be done. So in a reinforcement learning network, that can be, people have done a little bit of work where they've looked at sensitivity to reward and punishment, updating of aversive prediction errors. But there's an interesting literature that has been developed about how Pavlovian biases, aversive Pavlovian biases, alter subsequent learning rates in operant situations. The other element is there's, roughly speaking, in the computational world, two ways of thinking about how to actually solve a learning or decision-making problem. One is to think of it as a value-related problem, where what you're trying to do is you're trying to maximize, Bellman's equation. You're trying to maximize your values over a long period of time. The other is an inference problem. And the way to think about that is you're trying to optimize how correct can you be within the statistical environment that you're presented with. And they can, in many cases, and quite frankly, the direct comparison hasn't been done, which one is a more appropriate framework for a particular problem. But it's roughly speaking that you can think of this in terms of, again, reinforcement learning and active inference. And I just want to walk you through sort of how one could think about this. So, for example, when you look at value-based decision-making, and I focused on addiction anxiety, you could think of, and now coming back to aversive-related decision-making, you could think, for example, in addiction, as you have state actions and outcomes, right? So that we heard about the previous, Q-value learning. And you can think of the states as being, say, there's a certain value of being intoxicated, and you have actions available either to take the drug, to stay intoxicated, or not to take the drug, which would get you into the abstinent state. And of course, then you have the same options there. And the notion is that, even in addiction, the predominant notion is that people take drugs for positive reinforcement reasons. In other words, they want to stay intoxicated. But actually, another way of thinking about it is people take drugs because they are aversive of the withdrawal symptoms that come when they're no longer intoxicated. So then the selection is not about making the sort of you're intoxicated more likely, but is making the abstinent state less likely. So that's one example in the addiction side of things of how to think about negative reinforcement and aversive related decision making. The same thing in anxiety here is you can think of if in a social anxiety context, say being alone has a certain value and being affiliated has a certain value, but the approach behavior, the action associated with that has may be associated with negative consequences or the possibility of rejection. So the point is that the agent in a social anxiety disorder may actually select an action not because they think, oh, it's great to stay alone, but because they're trying to avoid the negative consequences of being rejected if they're in an affiliated state. So that's just a way of putting together or making this concrete with respect to say a psychiatric state. Somehow this doesn't. Let me see whether I can. Oh, yeah. Maybe. So from an active inference work, and again, I don't want to belabor this too much, but now you're looking at the same situation, but from a slightly different framework. Here you have you're trying to make inferences. You're trying to make inference from observations. And in addiction, you have, again, you have the states that is abstinent and intoxicated, and you have the observations that might be you feeling calm or you feeling irritable. And then you have policies that transform these, that gives you actions available that make you go from one state to another. And again, whether it's in the addiction context or in the anxiety context, the notion is in a negative reinforcement context or in an aversive decision-making context, you're not doing it to maximize a state, but you're maximizing the avoidance, you're minimizing the presence of an aversive state. Yeah. Oops. Let me just go back to. And again, this is sort of a way of conceptualizing and bringing to sort of a really clinical scenario how you might think about computational processes in, say, addiction and anxiety in this particular case, but also maybe in other disorders. And so then we thought in terms of again, within the active inference context, what could be failure modes that would be particularly relevant for anxiety? So I'm going to walk you through this just very quickly. So there are two possibilities to think about. So in an active inference context, of course that's within the Bayesian context, you have prior expectations. You're making observations and you're updating your priors to posteriors, which then become the priors again, so that you can then make more adaptive decisions. But there could be two problems. One problem is that you might have what we call hyper-precise priors. So what is that? That means that you're so sure that your distribution over the possible states that you can have are so precise that they don't allow for things to actually occur. And what that, and I'll show you in a moment what that does. And the other possibility is that you have what I would refer to as context rigidity. And we talked yesterday about this a little bit. David called it ethology, that in different contexts, people may be using different problem-solving procedures, and it could very well be that basically individuals are unable to adjust their the components of the Bayesian updating based on the context. So let me just walk you through. So how would this work out? And we put this in the context of interoceptive processing as well. Say you are somewhere in a kind of wooded environment and you hear a sound. And your prior model is, okay, the sound could either a rabbit or a bear. And so that then, based on your prior, you actually create a perception. And the perception is heavily weighted by the interoceptive association, the heartbeat rates and things of that nature that come with the sensory stimulus. So then basically what happens is let me see. Oh yeah. So then you actually see, this is just a rabbit. It's not a bear. And so in a healthy brain, what you would expect, of course, is that in the subsequent encounter, you have a much more higher prior for the rabbit. So you're basically once you get, again, uncertain evidence, first of all, your interoceptive system is much less aroused, and you're able to weigh in and say, this is most likely going to be a rabbit and not a bear. So on the other hand, in an anxious brain, we proposed that what happens is you might have a very strong prior that there's going to be a bear out there, and that you process that evidence, that uncertainty under this hyper-precise prior, and then what is important is that in that context, the actual evidence only marginally adjusts the old prior. So you really are not updating. So this would provide evidence that maybe there is some problem, possibly because of the hyper-precise prior, that your model is not getting updated. So that even the next time you're out in the woods and you hear a sound, you're still anxious, you're still expecting to see a bear and not a rabbit. And so the same thing, now let me just kind of, so the other alternative, same process, but this time now you're getting the evidence in a new context. And so what we think is going on in a healthy brain, there'll be some adjustment. It will be not, obviously, it'll be not exactly precisely the same prior, but some adjustment. But what happens is that in the dysfunctional brain, there's absolutely no adjustment to the new context. So those would be that would be the other alternative. So let me show you now what might be evidence, even though some of these studies are not within the active inference context. So this was a first study that we did now a number of years ago. And this was sort of motivated in a sense by a study that Michael Browning did a number of years ago, showing that anxious individuals have really a difficult time adjusting to the statistics of their environment. The idea is that and in particular, when I say statistics, to the volatility of the environment. The notion is that if something is rock solid stable, then any deviation from that rock solid stability should give you a clue something has changed. If something is highly variable, then just a little change could be, again, another example of noise rather than signal. So another way of saying this that anxious people have a difficult time separating noise from signal. So we did this in terms of experiment using a change point detection task that Angela Yu had published on and developed many years ago. It's essentially a sort of random dot coherence patterns on 3 different ponds or 3 different locations, and and the reinforcement is such that one area is more reinforced than another, and you have to learn about this, and then it's switched. So it's essentially similar to the reversal, but in this case you have 3, so it's basically a change point task. And so what we did is we basically created various models, and we compared various models, Angelus models, a dynamic Bayesian model, as well as a reinforcement learning model. What it turned out, one of the best models was a model that had 2 parameters, a base learning rate and what we call the learning adjustment rate. The learning adjustment rate was essentially a parameter that was in response to the volatility of the environment. Because obviously, if the volatility of the environment changes around a change point, and that should then your learning rate should go up. And so what we found, what was really interesting, is that high anxious people have a high base learning rate but a lower learning adjustment rate, whereas the low anxious people have exactly the opposite. And there were nice associations with direct observable behavior. What does that mean? It means that basically, and I don't show you, I'm not showing you a lot of other slides, but we showed that they were able to actually learn the statistics of the change point detection. But what this means is that anxious individuals overinterpret statistical fluctuations as a sign of meaningful change. Because if you have a high base learning rate, that means that you're more likely to change your behavior even if it's a random fluctuation. Because you shouldn't, there's a certain randomness that comes even when you're rock solid on the right pond or the right spot of the change point of the 3 dots of the change point. But once the fluctuation goes up, because now you're entering a change point regime, that's when you need to pay attention. That's when you need to ramp up your learning and say, oh, something has happened. The anxious people were not able to do that. So the question is, why is this important? Well, I think this is important because modern treatments of anxiety are based on relearning fear-related context or content. And so if there's a fundamental problem in how anxious individuals process these environments, then we really need to figure out, can we develop new behavior of pharmacological strategies to adjust that problem? So it becomes a new endpoint that we can then look at to see whether we can develop better interventions. And in a sense, it shows that the computational approach can parse into really interesting and precise ways how anxious individuals process information different than non-anxious individuals. So now I'm going to show you another study in a slightly different context, and I'm really excited about this because it's so deceptively simple. So let me tell you a little bit about what we did here. Actually, it's part of the same cohort. We've studied 1,000 people. The first 500 we've analyzed, and the subset of the first 500 is what you're seeing the data of here. I can go into detail. But we've developed a very, very simple task, and this came out of the optimal control theory literature. So what we have people do is they basically have a little car here, and the goal is to get the car as quickly as possible to this line, to the stop sign, but not over. If they get over, they get it's a missed trial. So the point is they have to accelerate really quickly, but then decelerate. So this is basically these actually the velocity curves. You see the acceleration, deceleration, acceleration, deceleration, acceleration, deceleration. And this is a classic sort of control problem. And there's been a system that has been developed for these classic control problems for a long time. And as was already mentioned, is basically, it's called, the full system is called proportional integrative a differential controller. And what it means, it just breaks down the error into different components. There's a proportional component, there's a differential component, and differential is obviously the difference of the error over time. And the integrative component is the integration, which would be the summation of the error over time. The reason why this has been this was developed actually in the late 50s, early 60s. This has been essentially, all of the things that we're using these days, like temperature controllers and things of that nature, use the PID model. So that's what keeps the room cool and whatever not. The other thing that so we basically applied this as a model, as a simple model of motor behavior, and then we were interested, was this in some ways related to anxiety? Now, first I need to tell you that these the nice thing about this task, as you can imagine, this is a continuous task. And we're getting data points on 50 data points per second. So you have massive amounts of data that allow you to get really, really good fits and determine and differentiate the different models. So here's, for example, I show you basically the data and the simulation from the model, and they're virtually indistinguishable. Again, the way that this works is that the position of the virtual car is controlled by the joystick, and then each subject completed 30 trials, and in each trial they were instructed to drive the car as quickly as possible to stop and as close as possible to the stop sign without crossing the stop line. That's what I told you. And again, we were basically using this model. Now let me show you why I think I'm so excited about this. So first of all, here I'm showing you the KD, which is the differential parameter, and the KP, which is the proportional parameter. I show you the KP and the KD for the odd and even trials for all the subjects, and you can see they are super tightly related. In other words, you can take the different trials, and they're very, very rock solid. What's even more interesting, you can take the first 5 trials and estimate the KPs and the KDs and compare to the estimation from the entire trial, from the entire 30, and you get almost the same estimates. What that means is you don't need a lot of data points, because you have really intense data points for each trial. And then finally, this is a plot of the recoverability of the KD and KP parameters. So what we did is basically we generated trajectories and see how much we were able to recover the KD and KP parameters for the different people. And they were immensely recoverable. So this is all good news in terms of underlying model. So then what we did is we built in, so the other thing we've been doing now is we're using hierarchical Bayesian model using RStan to come up with posterior estimates of all of these parameters. So what you see here is actually the posterior median and the credible interval for each of these parameters. This allows us really to do very effective model comparisons as well, because we can get WAICs and all kinds of measures out of these from these posterior distributions. So what we found is, and let me just summarize this here. We found that the KD, that there was a individual strong effect of the individual in terms of the variability, but that there was a significant effect of the PANAS, which is the positive and negative affect scale, fear component, and such that there was that the greater the fear, the lower that parameter. And what that basically means is that individuals with high levels of fear had decreased weighting of the kern error, which is consistent with an inhibitor goal approach, and also, and I'm not showing you this here, decreased weighting of the rate of change of error. Actually, I'm showing you the change of error, not the proportional measurements. What was nice, these findings were very specific to fear. We were able to control for negative affect, and what again is really exciting here, it's a very easy, robust, and reliable approach with motor trajectory. The other thing we did is actually have structure. We didn't do this task during imaging, which is what we're doing now, but we have structural imaging, and there was a nice relationship to various structures that are important for motor behavior. So using this PID framework, although for this particular case we use mostly a proportion in derivative control framework, we could parse altered error controls in individuals with anxiety-related problems. So in such a way that anxious individuals underestimate the error of the current motor actions consistent with increased inhibition, and then also underestimate the rate of change of the error, which results in oscillatory behavior, right? So I call this should I stay or should I go now? And this was really well replicated, or the models really well replicated the motor findings that we had with anxious individuals. So what's interesting about this, these parameters have direct relevance to treatment targets, because we know that increased inhibition and approach avoidance conflict, which I'm going to show you in a moment in a different framework, are a key component in anxiety. And so by now linking them to specific brain areas as well, we could begin to actually look at can we modulate this either by direct brain stimulation or by other types of interventions. So here's another example of how we're trying to parse the dysfunction in anxious individuals. So I told you before about anxious individuals have a problem adjusting to adjusting their learning rates to the different conditions. So what we wanted to do here is we wanted to see whether the exaggerated surprise to predictable events, which is sort of what was consistent with the first studies, is it due to a learning problem or is it due to a perceptual problem? And so in order to kind of try to differentiate this, we created sort of a hybrid, basically reinforcement learning model together with a drift diffusion model. And what that does is, we were using more of the data. In the first experiment that I showed you, we used basically the choice that they made. Here we used the choice that they made plus how long it took them to make that choice. So we used also the response latency. So what we did is we basically built a drift diffusion model where the boundary or the drift rate was basically estimated and updated based on the learning parameter. So this allows us to really see, is it learning or is it the drift rate that actually is dysfunctional? And so then we compared 6 different models that had whether it was bias with a single learning rate, a dual learning rate, and so on. What we found is that really the dual model best predicted the behavior. And then again, we used the hierarchical statistical model and related back to the PANAS. And again, what we found is that it was essentially the perceptual fear slope, which has to do again with the drift diffusion model, that was related to fear, and it was not the decision fear slope that was related to fear. So that was basically not significant. This was significant. So what this tells us is that it may not be a decision or learning deficit, but it could be a perceptual deficit. And so the other nice thing is we computed some interclass correlations, which were actually relatively high, which also make us more excited about using this framework. So again, essentially, the slower updating of the internal model is probably due to perceptual processing, but not due to decision making. So that we were able to use these models to separate the decision and the perceptual process, and that one of the things is that maybe what we need to be focusing on as we're developing treatment is to modify anxious individuals' perceptual processes rather than their decisional processes. So finally, I want to talk a little bit about anxiety and active inference framework. So this is work that Ryan Smith has been doing at our institute. And this was based on work that had been done before in a non-modeled approach by Robin Opperly at the Institute, focusing on approach avoidance conflict. So we know that approach avoidance conflict is a big issue in anxiety. People have a difficult time arbitrating in situation where there's both approach and avoidance. So what does that mean? Let me show you the paradigm. The paradigm is fairly straightforward. We have a little agent here, and basically the agent, you position the agent, and as closer you position to one or the other side, the more you get a certain outcome. And the outcome basically is either positive or negative, and it's associated with a certain reward. Now, we have several different trial types. In an avoid threat situation, you have basically a negative outcome, which is sort of a ghastly picture here, and a positive outcome, which is a nice picture. So of course you go over to the nice picture to avoid the negative outcome. In an approach reward situation, you have basically two positive pictures, but this positive picture is associated with some points that you can later on cash into money. And then we actually, then we create conflict situations where essentially you have the nice picture, but you have no money, and you have money, but you have the ghastly picture. And so you have to basically decide how close you want to get to the ghastly picture. Again, the closeness is related to how likely you're actually going to encounter this outcome. So that's basically the task. Again, the goal is to try to make as many points as possible. So what Ryan did, he modeled these different states, because of course, and again, many of you may be familiar with the active inference framework, but I just want to briefly outline what you basically generate. You generate a complex state space, and then you prescribe various Markovian matrices that quantify the relationship between the observation and the hidden states, between the current and previous states, and the preferences of the agent. And if for these matrices, you parameterize them by basically, he parameterizes them by two parameters, which is the emotional conflict and the decision uncertainty. And so then we were looking at various instantiation of the model and compared the model and determined which parameter was most likely related to anxiety. So what we found, and here's actually, I want to just focus on this group. We actually also compared this to a substance use group, but I just want to focus on the depression anxiety group, which is essentially this mixed Ardokian group. Individuals with depression and anxiety related problems showed greater decision-making uncertainty relative to healthy controls. That's this decision parameter. So you can see here that this parameter is significantly greater than the healthy controls. There was no significant difference in the emotion conflict parameter. So how do we, and then what's important is that actually this decisional uncertainty was actually related to the subject's self-report. So you can see a couple of, we basically had a post-task debriefing, and you can see there's a nice relationship to some of these questions that the individuals addressed. So what was nice about it, which again I didn't show you all the details, the model showed high accuracy in predicting behavior. It showed a strong relationship to the subject's response times and to the self-reported feelings and motivations during the task, which I showed you. And what's interesting is basically the beta was really uniquely associated to decision-making problems, and it was the beta that was most different in the depression and anxiety group. Lastly, both of these parameters were not highly correlated, which is also important. So in general, I know I walked you through a lot of things, but what I wanted to say is that we're able now to begin to talk about these computational failure modes in anxiety. And again, we need to come up possibly with a better term. But what are the things that we've identified? Well, we have shown attenuated error control. That's the first task that I showed you where they couldn't adjust their errors. Attenuated updating of incoming sensory information, and exaggerated processing of uncertainty. Now, Do we know that this is all the same? We don't know this yet. We know that in some of the tasks we see deficits. So in other words, what we need to do now is do all of these tasks in the same subject and see whether these errors, these dysfunctions are correlated. We are able to say with fairly good uncertainty, certainty that these dysfunctions are really related to anxiety and not to negative affect. For all of the models that we've created, particularly the hierarchical Bayesian models, we always include also negative affect. So it isn't that it's just they're feeling bad. This is really specifically related to anxiety. What's important here also is these failure modes can be readily assessed with behavioral paradigms. I really have in mind that some of these paradigms could be transitioned into the wild with mobile phones and things of that nature. We have some initial evidence, and I didn't go through this, that they are associated with distinct neural circuits, and that because of the nature of these dysfunction, we can begin to develop specific failure mode interventions. That's the way I think about it in terms of where does this lead us on the actionable side. We need to identify these failure modes, and then we need to identify interventions that directly address these failure modes. So lastly, in 1 minute, I just want to put I have 5 minutes? Okay, good. So I have 5 minutes. I want to put a plug in. I think we need a good, large community. And I really want to emphasize that Quentin has done a fantastic job. I know many of you have probably participated in the Transcontinental Computational Psychiatry work group. It's an online, once a month forum where people can present their work. I think it's a wonderful opportunity for people to connect up. And I think we need a community because the problem that we're trying to solve is really a big problem. And let me show you how we sort of think about this. So again, this is what I think of when I think of computational psychiatry. I think, how does the system work? That's what we're trying to figure out. And what does that mean? Identify mechanistically interpretable parameters, right? Psychiatrists are still stuck in Freudian explanations of the 19th century, right? I mean, it's like, and I'm not meaning classical psychoanalysis, but I mean actually in terms of thermodynamical explanation of how the brain works. We need to go beyond this. So that's what I'm hoping this can do. We need to also integrate measures across units of analysis. That is a hard problem. I can tell you that's a hard problem. From having done this, and I see a lot of head nodding, having done this, the variance accounted for when you go from one level to another level is unfortunately not very large. And we don't have a good answer why that is. That is actually what I would call one of the key problems. If somebody has a good idea and can actually show why that is, why can we only, if we look at imaging and we look at behavior, why is it that we can only account 10% of the variance? That could make a huge difference. It's a very hard problem. But then eventually we want to classify individuals into different classes of failure, what I would call now failure mode, and separate health from pathology, because ultimately we want to develop new actionables that make people better. That's and then obviously we want to predict class membership. I didn't talk about predictions a lot, but once you have sort of this model laid out, then you can ask, okay, so who is a person who's likely to perceive things, to misperceive uncertainty, and therefore potentially develop anxiety-related problems? Because we want to get the people before they develop the problems, and prevent bad outcomes. So I would see these as the main goals. And the reason why this is so a couple of years ago we put this together in a little paper, and the way we kind of envisioned this is sort of similar to kind of drug development. We have different phases. We have a preclinical phase, phase 1, 2, and 3, and 4. So what does that mean? It means that in a preclinical phase, which is a lot of people that are sitting here that are supposed to be helping us, we have to identify the probes, the measures, the models, and the potentially interventions that actually give us the failure modes that we can work on. And then part of this, we have to establish reliable, robust probes measures. That's a big task. I mean, probably many of you know the work that Russ Poldrack's group has been doing in trying to identify what is the ontology of our behavior. And one of the unfortunate outcomes of, unfortunate but true outcomes of this is that many of our probes currently have relatively modest reliability. And modest is actually a kind of a euphemistic term. But what does that mean? Reliability puts an upper limit as to what you can measure in repeated measures designs. And if you ever want to do an intervention, you have to have repeated measure designs. So we need to really identify what are our reliable and robust probes. So, and that's a big task. And then, of course, we need to see, do we have a target engagement, all these other things. This will require, no one lab can do this. It really has to be a community. And that's what I'm hoping we can ultimately kind of build, is a community of people with different expertise. And as you know, we've heard a lot of different approaches over the last 2 days already. No one person has the expert matter knowledge to really bring this together. We need a group of people. So I think I've walked through this. Yeah, so the way I see this ultimately is that computational psychiatry essentially can be at the base of both of those sets of questions, you know, of the explanatory and the pragmatic. I didn't talk about the pragmatic, but there's a clear a branch that also links back to, and you know, we have obviously heard other talks about this over the last couple of days. But I really think that computational psychiatry can be a base for this and can help us build better disease models, generate better, more accurate and robust predictions, and then help us change people's lives. That's ultimately what we want to do. So I want to thank you for your attention.